Hello class, so this is CSE 5250 section 2 and we're currently in week 5. Let's begin by taking a close look at the syllabus again, because I may need to make a few changes in light of a few things that has happened in section 1. So, we're supposed to be looking at Nvidia CUDA, but due to a few things that I'll explain later on, I'm going to be switching instead to MPI. I'll link to a few tutorials on how you can use Nvidia CUDA, but I may just end up dropping the Nvidia portion. No, rather, I may just end up dropping the Nvidia CUDA assignment from the course. But for those who are curious, maybe just stick around and maybe I'll explain how you could make an Nvidia CUDA program. But for now, first I want to look at a few more example programs that we could use instead, or rather, a few more example programs that we can make parallel. Well, here they are, or rather, here's the tree I'm talking about. The first one is, well, the Pythagorean theorem. This is famously stated as a squared plus b squared. No. This is famously stated as a squared plus b squared equals c squared, and we're looking for what's known as a Pythagorean triple. It is an integer solution, or rather a whole number solution, where a is a whole number, b is a whole number, and c is a whole number. And when you put them into this formula here, it results it results in a squared plus b squared equaling c squared. So, what does this program look like? Well, I have it open here, so let's run this and see what I'm talking about. Here we are. So what this program is doing is running a triply nested for loop where the I, j, and k ultimately are used to plug in as values for a, b, and c. And here we have a solution. 3 squared plus 4 squared equals 5 squared. This means 9 plus 16 equals 25, because 3 squared equals 9, 4 squared equals 16, 5 squared is 25. So when you add 3 squared, which is 9, to 4 squared, which is 16, you have 25, which is 5 squared. So that constitutes a integer solution, no, a whole number solution for the Pythagorean theorem, where these whole number solutions are known as Pythagorean triples. So this is a program that can look for Pythagorean triples. Now, I limited the search for this program to 100, but you can toy around with this and see how fiendishly slow it gets when we try increasing the maximum search here. So here, it's running even slower because this is a triply nested for loop. So we're looking at a runtime that's on the order of big O of n cubed. This is slow. But it can be made even slower if we just increase our search max. So you can play around with this to try to make it parallel and see if you can get any sort of reduction in execution time. That is, see if you can make the program any faster. And that's just one example. There are 2 more examples in here where instead of a squared plus b squared equals c squared, we're either subtracting a times b or adding a times b. So where does this come from? Well, let's see. If I can find the... If I can find the link, then give me a minute. Okay, I found it. So here's a journal article that explains where these variants of the Pythagorean theorem came from, and these are variants that work for 60-degree and 120-degree triangles. So, the short answer is the Pythagorean theorem is a special case of what's known as the cosine rule. So, a squared plus b squared minus 2ab cosine gamma, and this gamma angle is the angle that is directly opposite of the C side of the triangle. So, in a standard, in a regular right triangle, this gamma corresponds to the right angle that's opposite of side C. So, normally, in a right angle, gamma is 90 degrees, and the cosine of a 90-degree angle is 0. So, naturally, this begs the question: is there any case where cosine of gamma is... Okay, I'll just cut to the chase. If gamma is 60 degrees, then cosine of 60 degrees is 1/2. So this results in a version of the Pythagorean theorem where a squared plus b squared minus ab equals c squared. And in the case where gamma is a 120-degree angle, cosine of 120 degrees is negative 1/2. So this results in a version of the Pythagorean theorem where a squared plus b squared plus ab equals c squared. And so those two other example programs I have here are looking for whole number solutions where a squared plus b squared minus ab equals c squared, or a squared plus b squared plus ab equals c squared. So there are two more example programs that you can use. You can play with these. You can try to make them parallel. You can look for whole number solutions. I won't be showing you what these solutions are because I kind of want you to find these solutions for yourself. But they're here. You can play with these programs. You can try to make them parallel. These aren't part of your assignments, but I encourage you to play around with these programs. Now, the next part is supposed to be how you can set up Nvidia CUDA on your own machine. I had in mind where we can write an Nvidia CUDA program regardless of whether you have the necessary hardware. So if you have a computer and you know for sure you have an Nvidia graphics card on it, you can basically just skip ahead to the Nvidia CUDA toolkit installation instructions. Install that, and you can basically run. You can basically write and then run an Nvidia CUDA program. If you don't have a computer that has the necessary hardware, the fallback was to access the Jack Brown Hall computers. The fallback was to access the Jack Brown Hall computers remotely, write the programs remotely, and then run the computer, and then run the programs on Jack Brown Hall. But the problem was, I don't think they're set up yet. So, if it's the case that Nvidia CUDA isn't set up on the Jack Brown Hall computers at all, then we may just have to drop the Nvidia CUDA assignment altogether and just try something else. So, for those of you who want to go forward anyway with Nvidia CUDA, basically the installation instructions require you to look for the CUDA toolkit. So, this is what it would look like. We search that up, developer.nvidia.com to CUDA toolkit. We download. Here we are. download now. You would choose the installation that matches up with the computer you have. So in my case, I have Windows 10, and then I would just download this installer, run the installer, follow the on-screen prompts, and hopefully not have it break anything else on my computer, because I tried to record myself installing this and it actually broke the recording, so I don't want to show that process again out of fear that it would break out of fear that it would not be able to be recorded. So you would just follow these instructions. You would then have Nvidia CUDA installed on your computer. You can then run Visual Studio 2019, create a new project, and then you would have the option to create a CUDA program. So we would just select that, click next, and then it would just set up a Visual Studio project. And this is the default program that and this is right here is that this is the default program. So maybe for those of you who want to try something else, hopefully by the time you watch this, there should be a link to an Nvidia CUDA tutorial, which should look like, well, this. By the time you watch this, will have included a modified version of this Nvidia CUDA program here. But you can just copy this. You can just copy all that code, paste it into here. In the world of Nvidia CUDA, and CUDA, this is a runtime invented by Nvidia for making parallel programs. So what's going on in this example program is we're trying to add two arrays and having the result. Yeah, we're trying to add the values in one array to another array. So this is done by a for loop, and we can just make a special function that Nvidia CUDA that can be used using Nvidia CUDA. What happens is you're basically launching what's known as a kernel on the GPU. This is Alright, you know what? Let me just pause this and then I'll pull up my own example. Alright, so I changed that code, and here's what we have. Alright, so here we have a special function that we have to add we have to add global to. In the main function, we have to allocate memory, as much memory as we need for X and Y, because this is a separate device that has its own memory, so we have to allocate the necessary memory. Here we're just populating the two arrays with 1s and 2s. Those add up to 3. And then we run the kernel, and it's going to add two arrays one filled with 1s and the other filled with 2s. We run that. We call CUDA device synchronize. This section of code just makes sure that everything worked. And then we free the memory that we had allocated previously. That's the short version of it. And again, I'll be linking to a tutorial that explains it all in greater depth. So for those of you who want to forge ahead anyway with Nvidia CUDA, I won't be asking you for an Nvidia CUDA sieve anymore, but the option is there if you want to try it. And with that, I'll be going through a tutorial on MPI instead. Simply because Nvidia CUDA is causing problems, and I just wanna go ahead anyway with MPI in the meantime. Right, so Professor Lawrence Orijuela provided these instructions for me, so these are the instructions for installing MPI on Visual Studio. You only need to do this once if you haven't already. Once you've done that, you're gonna have to follow through these instructions to set up a Visual Studio project that uses MPI. Now, running an MPI program requires a few more additional instructions. And all this is just a setup for the Visual Studio project. It's a bit more in-depth compared to OpenMP. So, maybe I can just demonstrate it for you. I'll make a new program. No, I'll make a new Visual Studio project. New project. Come on now. We'll just make it an empty project. No start files at all. Next. I'll just call this CSE-5250 MPI example program. And that's what we'll be calling the program. It's a bit more in-depth compared to Nvidia. It's about as in-depth as OpenMP, if not more so. Now, let's add a source file, main.cpp. And now, I have an example program whose contents I'll just simply copy-paste. You should have access to this program as well, but here it is. We'll just copy all of that and paste. And now the program, Visual Studio doesn't know what to do. And that's because we have to follow a few setup instructions, which I will demonstrate here. How to make a C++ project on Visual Studio. And for every new MPI program we have to make, this is what we need to do. Right, so project, properties. I hope you can see this clearly. You may need to zoom in on this, but I don't know how to. Anyway. Okay, we have to include mpi.h, but we've already done that. Click the project tab and go to project properties. Include the MPI directories, so C/C++. Additional include directories, edit, and then we have to add now wherever you installed MPI on your computer, you're gonna have to find that. selector to navigate to this. Okay, so here we have to navigate to wherever we installed MPI on our computers, so let me just find that. Let me pause the video. Okay, so in my case, I have to go to here. Local disk, program files x86, Microsoft SDKs, MPI include. So that's the directory I need to include. I'll copy that. And here we have to include that folder, so I just copy that entire link and paste that in. It's this include folder that we have to include, so add that. And we're not done yet. Then we need to go to linker, additional library directories, edit that, and now we have to select another directory. Now here we need to, instead of the include directory, we need the lib. For our purposes, we can just get away with the x86 folder. Select folder, add that, and additional dependencies. On the left side of the property pages window, under linker, go to input, additional dependencies, edit, and then we have to add in msmpi.lib. What? I misspelled it. Apply that. And there we go. All of that just to make this program work. So, how do we run it? Well, thing is we can't just run it using the local debugger. Instead, we have to run it using the command prompt. So, how do we do that? Well, first we have to navigate to the directory that contains the exe file for this program. So, first off, we need to build this program. Let's see. Build. We can just press Ctrl-Shift-B and that will just build the program for us. And now, we have to click here, up here, and open folder in File Explorer. That's the wrong one. Open folder in File Explorer, and here we are. Now, there's a debug folder in here, and that contains the exe file. We want to run, we have to use, we have to run this using command prompts. So let's go into this address bar in here and type in cmd. There we go. Now, we can just type in a simple command, mpi exec -n. Let's run this using 4 processes, and then we have to enter the name of the executable file, which is CSE-5250 mpi example program.exe. And there we go. Now this is for Windows. For a Linux system, it may be a bit different. But I'll get to that a little bit. I may elaborate that more in the next video. But let's exit this, and let's try this with PowerShell. It turns out we can just use the same command here. So exec -n. Let's try four processes, and the name of the executable is CSE-5250. And it also works with PowerShell. Now, the point of MPI is to run a program, a multi-threaded program, among multiple processes, among multiple computers. Here we're just restricted to just one computer, but there is a way of making it run on multiple computers. I'll explain more about that later on, but for now, this is just the basic setup. Needed to just make an MPI program and make it run on however many processes that we want. So that's the MPI tutorial right there. Now this recording is a bit short, but hopefully that will be enough for you to get started with MPI. We'll have to circle back around to Nvidia later on, but for now I'll just end the video here. But if you have any questions, you're welcome to email me about it. So I'll stop the recording here, and we'll meet up again next. We'll pick up from here next week and see how we can use MPI to make a multi-threaded Silva Veritasinis. So I'll end the video here, and I'll see you next week.